Okay, so here we are. So this is, of course, our last class. There's only really one thing left to do. I've written and I put them on Moodle yesterday, so we can work on these today. It's a small series of practice problems for hypothesis testing that will give us another opportunity to go through the process step by step and see how this is done. We can do it both the traditional way, which means we compare the test statistic to the critical value, and we can also use the p-value approach. So this way we'll have a complete practice of the process for both testing hypotheses about means and for proportions. All right, so let me just go get Moodle open here. And while we're at it, let's see what else is on there. All right, so the extra questions are down here. Everything else should be here. Everything that you need for the course, I believe I'm completely caught up. We've got the last two problem sets, 9 and 10 are here, along with the notes. And yeah, I believe it looks like everything's here. So we'll start this today, or actually we'll do this today, just to get some extra practice. And then we'll be done with the course, believe it or not. It seems like we just started, doesn't it? Yes, it does. But of course, it's a very, very heavily condensed version of the full semester version of this course. We're doing this in 4 weeks instead of 16. So of course, it seems like we're going very quickly. But so far, everyone seems to be doing very well, which is good. But also, let me just go see if there's any announcements here that I think I may have put one in here. Yeah, it's being a little stubborn, as you can see. Yes. Oh, I guess this was just a quick reminder. The final exam will consist of just the chapter 8, 9, and 10 problem sets. So what if you've already done chapter 8, which was due on Monday anyway, that would leave you just the 2 problem sets, and those would be due on Monday the 5th. Okay, so now I know it's a long holiday and all, so you can have until midnight on the 5th. That should take care of it, and then I'll hand in the grades the next day, and then we'll be done, and that should take care of everything. So you'll have your class done, and you'll have 3 credits knocked off for the fall, and you'll also have a lot of knowledge of statistics that you didn't have before. So I'd say these were 4 weeks well spent for everyone. All right, so in the meantime, let's just take a look at these questions. So here we go. So here's number 1. PepsiCo wants to ensure, let me shrink that up just a little bit, that its 2-liter bottles of Pepsi are filled correctly. If not, the manufacturing process will be changed. Okay, so this is pretty important because if the bottles are underfilled, they could get into trouble with the FDA because they're trying to claim that they have a certain amount of soda when they don't. But if they're overfilled, they can explode on the shelves. And so they've got to make sure that they are indeed filled with 2 liters of soda. Now, it's never going to be perfect. Okay, there's always going to be some deviation from one bottle to the next, but we want to keep it down to a minimum. So we're hoping to find with this test is that we cannot reject the null hypothesis that they do in fact contain 2 liters of soda. In other words, the discrepancies are so small that we don't have to worry about it. So we'll pick a sample of 90 bottles, and the sample mean turns out to be 1.97 liters, and the sample standard deviation is 0.08 liters. So we have to test the hypothesis that the mean volume is 2 liters at the 5% level of significance. Now, the way it's written, I just want to give you a hint here. This is meant to be a two-tailed test. Okay, how do you know that? Because we're trying to find out if the bottles contain 2 liters or not. In other words, less than 2 is a problem, greater than 2 is a problem. So therefore, we're going to use a two-tailed test, and this way, whether the bottles are underfilled or overfilled, either way, we'll find out with the test. Now, here's the challenge today. Since we need the practice, what I would like you to do is, before we go any further, I hope you have a piece of paper in front of you. What I think you could do for some good practice is write out, before we go any further, the null and the alternative hypotheses. Okay, and then we'll do the same thing for all three problems. I'll have you work on it first before I tell you what the right answer is. All right, so first let me save this real fast. So, all right, go ahead and write down. Now, I gave you a bunch of hints already, so you should have no trouble figuring out what the null and the alternative hypotheses are. All right, so hopefully you wrote down the null is that the mean equals 2. And the alternative is that it does not. It is indeed a two-tailed test. Okay, now the level of significance, part C asks for the level of significance. That's pretty straightforward. So I'll just fill that in. Oh, whoops. No, it didn't ask that, did it? Oh, I'm reading things wrong here. No, it's the test statistic that comes next. All right, so what I'd like you to do is figure out the proper test statistic to use and then actually calculate it. Okay, so why don't you take a minute and figure out, first of all, which test statistic should we be using? And secondly, what should its value be? By the way, I'll give you a helpful hint. In the problem, they give us the sample standard deviation. There's no mention of the population standard deviation, so you can assume that it's unknown. We wouldn't need the sample standard deviation if we had the population standard deviation. So the mere fact that they're telling you what it is enough to suggest that the population standard deviation is not known. All right. So there's two possibilities here. So it's clearly the second one that we're going to use because we don't know the population standard deviation, which implies that we're going to use the t-distribution. So let's calculate. Now, the actual value of the test statistic is no different. That actually is irrelevant. The statistic will be the same, but what will be very different is the critical value. That's when it really starts to matter a great deal, which distribution we're using. So we've got X bar, which as you recall is 1.97. We're comparing that with 2, the hypothesized value of the liters in the bottles, and the standard deviation is 0.08, and the sample size was 90. Okay, it says there's some error. Yeah, there it is. The sample size is 90. So you throw that into your calculator, and when you're done, you should get approximately negative 3.56. Now that's a large number. That's 3.56 standard deviations below the mean. it already is fairly clear, although we need to go through the formality of proving it, that we're going to reject the null hypothesis. As a rule of thumb, let me just throw this in here. A rule of thumb is just a quick way of looking at a problem. If the test statistic is greater than 2 or less than -2, it is highly likely that we will reject the null hypothesis. It doesn't prove anything. It's not enough by itself, but it's very suggestive. So here with -3.56, that tells us that there's a very strong chance that we're going to reject the null. And that's trouble for Pepsi because that means that the bottles are not being filled correctly. But let's prove it. Let's calculate the critical value. Now, how is that done? Well, remember, there's only 2 sets of critical values. Let's just quickly review them. If sigma is known and sigma is unknown, in the case of the two-tailed test, we'd have plus and minus z alpha over 2. Over here, we'll have plus and minus t with n-1 degrees of freedom. Also, alpha over 2 is our region in the tails. Right-tailed, we just have simply positive z alpha or positive, well, we don't need the positive sign then, but it's positive z or positive t. But remember, it's now alpha, not alpha over 2. And left-tailed would be negative z alpha, negative t and -1 alpha. So in our case, since we're using the t distribution due to the fact that we don't know the population standard deviation, and it's a two-tailed test, that means this is what we're looking at, 2 critical values. Now, how do you find them? We can use a table. Now, this is where tables get a little awkward. The problem here is that the sample size is 90. And that means that the degrees of freedom is 89. And for the most part, so this is 89 degrees of freedom. Half the tail area is in either tail, 2.5%. The table is highly unlikely to contain a row for 89 degrees of freedom. If it did, well, you know, what sometimes people do is they'll take and round it to the next closest level. I don't know if that's such a great idea. So what we're going to do is use our calculators. We have them, we might as well put them to good use. So we have 2.5% in either tail, and these shaded regions represent the so-called rejection region. Okay, so you know, we can look at the table if we want to, but it's not likely that the answer we need is there. So why don't we? Well, first I'll show you that. So what we're looking for in this chart is 5% total split up between the two tails. That would be this case. But if we scroll down and look for 89 degrees of freedom, it's not there, is it? We have 80 and we have 100. So what do we do about it? Now, that would leave us with a value that is roughly halfway in between these two. And that might be good enough for many applications. We could actually go ahead and average those out and you'd get 1.987. But I'll tell you what, why don't instead, since we have our calculators, we'll go ahead and look up the exact value. So using the table gives an approximate value halfway between those two that we just looked at, 1.987. And we kind of got lucky here that we're halfway in between. If we had, like, say, 86 or something like that, it would have been a lot more difficult. Using the calculator, though, we're going to do second vars, and then INVT. INVT. Let me go get mine out. INVT is number 4, and then it's going to ask you for the area and degrees of freedom. So in a case like this, what you should probably do for the area is use, because, well, let's see, because we have 2.5% in either tell. Let me just quickly repeat this. That implies that everything below this point, including the bottom, the lower tell, adds up to 0.975. All right, we do not, we go all the way down to negative infinity. So put for the area 0.975. And then for degrees of freedom, of course, 89, 1 minus the sample size. Sorry, and then it will give us the exact values. So 0.975 combined with 89 degrees of freedom is, well, what do you know? It's almost exactly the same, 1.987. So this time it wasn't, well, we could have used the table, I suppose. But in many cases with these tables, you're probably better off using the calculator. That's good. All right, that's fine. Now, the p-value is the interesting part. For this, you absolutely should use the table. I mean, sorry, not the table, the calculator. You can use the tables, but you're only going to get a very rough approximation. So the p-value refers to the relationship between the test statistic, which, remember, is negative 3.56, and the area under the curve. So what you're going to do here is calculate the total area in the left and the right tells. So what you can do then is go to your calculator, and you're going to get, let's see. So you can do this in a couple of different ways. If you go back to second vars, the function that you actually need is called tcdf, and it's going to ask you for the lower limit, which is in this case negative second comma 99 for negative infinity. The upper is negative 3.56. And they want to know the degrees of freedom, which is 89. And if you plug in those numbers, you'll get, okay, it's a tiny, tiny little number, 0.000, well, 2989, let's say. So that's the area in either tell. You have to add these up, and this only is true of a 2-tell test, by the way. 0.000, 2989. So that works out to be roughly 0.000 5978. All right, now that's a small number. So the conclusion then, and there's two different ways of looking at it. The test statistic, if you look at this graph again, in fact, let me steal that and bring it down here. The test statistic is well out in the rejection region. So actually, maybe I'll just start this all over again. There's two reasons why you can conclude that we should reject the null. Number one, using the traditional approach of test statistic and critical value. So the test statistic was actually negative 3.56. The critical values were plus and minus 190, 1987. And so with the test statistic of negative 356, the test statistic is in the rejection region. Therefore, we reject the null hypothesis. In addition, the p-value is 0.000 by 978, which is well below the level of significance of 5%. This means that we should reject the null hypothesis. So basically, we've done it in two equivalent ways. Either way, we're going to get the same result, which is that we should reject the null. And then at the end, does that mean that we should change the manufacturing process? The answer is yes. Okay. Now, with all that being said, as an alternative, we can use the calculator as follows. So in other words, we just followed the traditional approach of calculating or determining if this hypothesis should be rejected. What do we do with the calculator? Well, if you go to the calculator under stat tests, keep in mind that we must use the t-distribution here. So if you do stat tests, we'll go to t-test, number 2, t-test. And that's because this population standard deviation is unknown. Once you get there, it's pretty much, and then use the data mode. When you're there, yeah, make sure you pick, the stats mode. And then it asks you for everything you could possibly want to know. Like, for example, mu0. What they're asking for here is the hypothesized mean. Let's see, there we go. Which in this case is 2. They're asking you for x bar, which I'll just write as x bar. The sample mean, remember, was 1.97, way back here somewhere. Yep, 1.97. And then it asks for the sample standard deviation, which in this calculator is written as SX. And that was 0.08. And then the sample size was 90. Now, the last thing you have to do is be careful to pick the right alternative hypothesis. All right, that's a key detail. Make sure you pick unequals. Okay, all right. Actually, it's been my experience that the symbol box takes forever to search through. So there's a clever way of getting around this in Word. 2260. Watch what happens if I type 2260 Alt X. There you go. How clever. All right, so that's how I express the fact that this is a two-tailed test. All right, so now you go ahead and do the calculations. And let's do that. 2, 1.97, 0.08, 90, and you'll see, okay, now because of rounding, it did get a slightly different p-value. They're telling us that the t statistic is negative 3.5576 or so. And so their p-value is ever so slightly different than ours. 6.0259 e minus 4, which equals 6.0259 times 10 to the minus 4th power. It's the same thing. And then that means 0.0006029. So we had 0.0059. Yeah, you can see it's really close. The difference is that we used negative 356, which is a slightly rounded value, and they're using the exact value. So either way, we reject the null hypothesis. Okay, so you can use this as a double check, or you can go through the traditional approach. But the questions here, for some of these, you do need to know, for example, what the test statistic is. Even if you use your calculator, you still have to be prepared to explain what the test statistic is and how you got your critical values. So the calculator is fun, but it's not enough by itself. Let's put it that way. Now, by the way, I don't know if you noticed this or not. If you go back to your same test, t-test, leaving all the data in place, at the very bottom, where it says calculate, we can, on the calculator, we can ask it to draw the test statistic, the t-distribution, showing the test statistic and the p-value. So how do you do that? At the end, after all data has been calculated or entered, use draw instead of calculate. So, you know, we always, so far, every time we ran this, we used calculate, but if you look at it carefully, right next to it, there's an option for draw, and it actually draws a little picture. And you can see, I'm not sure how helpful this is, but it does draw a little picture of the distribution, the test statistic, and the p-value. So you can see visually what this result looks like. Okay, just in case, you might want to look at it. It's interesting. So in other words, they're showing us this, except without the critical values. They're just showing us the test statistic and the p-value. Because in principle, that's all you really need. All right, then. Now let's try this one. So there's an art gallery, and they're trying to decide if they should increase the amount of insurance that they have in their collection. Good idea. You never know what this stuff is worth. So they're going to take, and if they find that the average value is above 100,000, then they're going to increase their insurance. So they're going to pick a sample of 15 works of art, and we find that the sample mean or average value, it says here, is $1,500. Wait, not 15, sorry, 15 works. The sample mean is 102,500. The sample standard deviation is 1,200. So again, you know we're using the t-distribution. Test the hypothesis at the 10% level of significance that the mean price of the art is $100,000. Okay, now in this case, they only care if the mean is above 100,000. If not, they won't take any action. So we're trying to prove whether or not the mean is above 100,000, or in other words, we're trying to prove whether or not it makes sense to increase our insurance coverage. Now, obviously, that's going to cost more money, but we don't want to be caught short if crooks come into our gallery and steals our works. It does happen. There's been lots of art heists throughout history. And so you don't want to be that one who gets on TV because your art gallery was robbed. So the null would be, of course, that the mean is exactly 100,000. The alternative is that it is above. So this is a right tail test. The test statistic, now again, remember, we don't know the population standard deviation. Which implies that the test statistic is this. And then while we're at it, let's fill in the numbers. All right, so the sample mean turned out to be 102,500. The population mean is 100,000. The sample standard deviation is 1,200. And the sample size was 15. So that turns out to be approximately, hold on one second. That's going to be about 8.07. Well, I think we know what's going to happen here. I do believe that they need more insurance because, like I said before, the rule of thumb is anything outside the range 2 and -2 is going to cause us to reject the null. So I think we have a winner right here. But we still have to calculate the critical value. Now, because it's a right tail test and it's the t distribution, our critical value is t alpha with n-1 degrees of freedom. Now, remember, alpha is 10% in this case. I know we normally use 5, but this time it's 10. So, pay attention to that. It's not always 5%. Now, this one we can look up in a table. 14 should be there. But we can also look it up in our calculator. So let's go look at the table for a minute. 10% is all entirely in the right tail. So we're looking at this one. We go down to 14. Oh, it's right here. 1.345. Okay. All right. So we'll throw that in here. But we're going to confirm it with our calculator. Why not? We have it. I mean, it's possible to make mistakes when you look at a table. So from the table or from the calculator, use second bars, number 4, INVT. And when you get there, just like before, it's going to ask you for, hold on. Area and degrees of freedom. Okay. So in other words, by the way, let's draw the picture. All right. So make area 0.90. Everything below that point. Now there's the right tail, remember, has an area of 0.10. Everything below that is 0.90. And that's what INVT is looking for, the area below, not above. Okay, so 0.90. Degrees of freedom is 14 because the sample size is 15, and it's n-1. 1.345. Yeah, exactly. So we just confirmed what we already knew from the table, but it's nice to have a backup. You never know when you might make a mistake. And so this way, if you do it twice, you're not as likely to make a mistake. Now, what that means though, well, the p-value then is going to be crazy small. The test statistic, as we saw, is 807. Now, what the p-value represents is the area to the right of that. Since this is a right-tailed test, the p-value is everything up here. So in order to find that, you can calculate the probability. Actually, let me move this here. This is the same thing as saying, what is the probability that X, I guess we'll call it. No, actually, we'll call it T, 8.07, which you can get from your calculator. The function that you're looking for is second vars T CDF, which is number 6. CDF means that this is the probability density function or cumulative density function. Now, in this case, the lower limit is 807. Upper would be positive infinity. And the degrees of freedom is 14. So my guess is that this number will be really, really small before I even do this. So let's confirm that. Yeah, this is pretty much what I was expecting. 6.1860 E minus 7, which is 6 zeros, followed by 61860. Wow, that's a small p-value. That's pretty much what I figured. It's so tiny. Now, in a case like this, for all practical purposes, you can essentially just round it to 0 because that's really what it is. Okay, so since the test statistic, well, let's draw this all together in one place. The critical value is 1.345. The test statistic is way, way out here. Okay, so since the test statistic is in the rejection region, we can reject the null hypothesis. Additionally, and you don't need both of these, by the way, one or the other is enough. I don't want to give you the impression that you must do both. One or the other is good enough, okay? Because they're actually giving us the same information. Additionally, the p-value is well below the level of significance of 10%, so we reject the null hypothesis. And therefore, the logical conclusion of all this is that will the Gallagher increase its insurance coverage? The answer is yes. Okay, that was the whole purpose of all of this. Now, if you want to run through this with a calculator, what you're doing is once again stat tests, t-test. Make sure you choose t-test because we do not know the population standard deviation. Okay, so let's go get it. Oh, and one more thing, we have to ask for stats. Okay, so we'll copy, let me just copy what I had up here. Yes, it's exactly like this. I just have to change the numbers. Okay, so the mean in this case was 100,000. The sample mean, though, was 102,500. The sample standard deviation was 1,200. And the sample size was 15. But then keep in mind, this is a right tail test. So when you calculate this one, what should you get? So really the only two things we need are the t-statistic is 8.07, which is what we knew, and the p-value is listed here as 6.1975 e negative 7. And again, it's not precisely the same as what we got because of rounding, but it's awfully, awfully close. Okay, so this way you have two ways of getting at the same results. And so you should have no problems with this. Now, even if you use the calculator, you should still be able to answer these questions, except that the calculator will not help you with the test, the identity of the test statistic. In other words, it'll tell you a value, but it won't tell you how it calculated it. So you have to remember that. And it will also not give you any information about the critical value. It doesn't, for whatever reason, do that. So that's why this part you have to do. Now, here's one with proportions. Okay, so proportions are a little different because there's only one way to do these. Proportions always are based on the standard normal distribution. So what do they want to know? The university wants to determine if the proportion of commuter students is greater than 60%. If so, a new parking lot will be built. So we pick a sample of 70 students, of which 44 are commuters. Let's test the hypothesis that the proportion is 60% at the 5% level of significance. Now, in this case, we only care if the proportion is greater than 60%. Also, don't forget, we're using the symbol, the letter pi, to represent proportions. Not 3.141, but so this is a right tail test. Because we only need evidence that it's greater. If it's less, we'll just keep the same number of parking lots. Okay, the test statistic in this case is very different than what we've been doing with the means. In the slides, I wrote it in two pieces. We don't have to always do that. Let's just write it as one big expression. Okay, so the hypothesized value is pi 0 is the hypothesized value. And lowercase p is the sample proportion. Now, in the problem, they told us that out of 70 students, 44 are commuters. So that means that X is 44, N is 70. All right, X is the number of objects or elements, that have a certain property. The sample size is 70, so we have to figure out the sample proportion ourselves, although when we get to the calculator, you'll see that it will do that for us. All right, 44 over 70 is approximately let's call it 6286. So that is above 60. The question is it far enough above that we can justify building a new parking lot? I mean, let's face it, it's a very expensive proposition, I'm sure, and especially where we are, they must spend half their money paving those parking lots because they're always collapsing. I'm sure by now they're soft as can be, full of potholes. All right, so let's do this. So we plug in the numbers. So 1 minus 0.60 is obviously 0.40. I'll just fill that in directly. And then the sample size is 70. So when you throw that into your calculator, that should be approximately, let's see. All right, let me try that again. All right. I've got 0.488, which is a very, very small number. Remember the rule of thumb, 2 plus or minus 2? Well, it doesn't look like we're getting our new parking lot, does it? No, because the critical value in a case like this, based on the normal distribution, and the level of significance that they chose for us is 5, the normal 5. Now, we've seen this one before. We don't need to look it up again. You probably have this one memorized. It's 1.645. If not, what you can do is go to your calculator and go to INV norm. And when you get there, just tell it that the area, hold on 1 second, let me get this out, is 0.95, everything below that point. It will automatically assume that you mean mu0 standard deviation 1, which is correct. And that gives us this value. Okay, so that's your critical value. And so the test statistic, as you can see, is nowhere near that. So this is my rejection region. And so, well, I guess it doesn't look good, but so the p-value is going to be really high this time. Since it's a right-tailed test, we're going to be looking for everything above 0.488. So I like this system. Blue is a reminder that this is the p-value, not the rejection region. I don't know, it just looks cool. So this is my test statistic. So what you're looking for is the probability that z is greater than or equal to 0.488, which, as you know, you can get from your calculator by going to second vars normal CDF. And of course, you'll be asked for lower, upper, which is of course infinity. The mean will be 0. The standard deviation is 1. And let's see, I'm going to do that right now. All right, 0.488. Whoops. Upper is 2nd comma 99. And that's going to work out to roughly 0.3128. All right. So now we know that the p-value is supposed to be less than 0.05 to be rejected. It's not even close. So as far as the test statistic approach goes, here's our rejection region. But here we go. So the test statistic is not in the rejection region. In addition, the p-value is well above the level of significance of 5%. Therefore, we do not reject the null hypothesis. And sadly enough, that means no new parking lot, because there's not enough evidence that the proportion is high enough to justify it. Plus, you know how things are in that campus. If they start building a new parking lot now, it might be ready by 2028. No. But it does, let's just say it causes chaos for quite a long time. So they don't want to do this lightly. Let's put it that way. All right. Now, if we're going to use the calculator, we'll go to second vars. And this time we're picking oh, wait a minute. Sorry. What am I saying? It's stat tests. So stat test, now remember, there's no such thing as a t-test with the proportions. So what you're looking for is number 5, 1 prop, z-test it's called. Okay, so all you have to remember is how many proportions you're looking at. We haven't done any cases with 2 proportions, so you don't have to worry about that. So they're going to ask you for p0, which is obviously the hypothesized proportion, which is 0.60 in this case. This is what we're looking for. We think it's above 0.60. X, the number of students. Remember, we said back here, we took a sample and 44 out of 70 were commuters. So X is 44 and N is 70. And so, of course, we have to specify. Now, in this case, it is a right tail test. So we'll type greater than P0. And calculate. All right. And of course, it'll give us everything we need to know. So we have 0.60, X is 44, 70. Right tail test, calculate. And so the test statistic is the same that we got with a little rounding. And the p-value is 0.313, let's say. Yeah, that's pretty much what we got. 3128. Actually, it's the same. It's 3128. And then this shows that we should reject the null hypothesis. All right. So, that seems to be it. So this was a very thorough, I thought, review of every conceivable detail you could encounter when testing hypotheses about the mean or the proportion. So study these well. Now, well, you already have the final one. What am I saying? All you have to do, I remember now, is do these chapter 9 and chapter 10 problem sets. There is no final for me to post. Chapter 9 and 10 are all that remains. I will take the chapter 8, 9, and 10 problem sets, average them out. That number will represent your final exam score. Okay. But while you're doing those, at least number 10, you should have this in front of you because it covers every detail that you could potentially need. And, just as we went along, you notice we did more work than was absolutely necessary. So, just make sure you just answer whatever questions they are. And, you can feel free to draw the pictures. They're not absolutely necessary. If you are using your calculator, make sure it's clear how you got your results so that I can give you partial credits if something goes wrong. But for the most part, I think you should be fine. Let me just do one more thing. This is one of my pet peeves with Word. By default, it doesn't have page numbers. You have to ask for them. I think that is so stupid. How could you not want page numbers? I want to understand their thinking, but I can't. So I just put in the page numbers because this is a long document. What happens if you drop it on the floor and the pages go all over the place? Exactly. All right. Or if your cat knocks them over or something, that's why you have to have page numbers. So anyway, I'll post this as soon as we're done. And then now you do have until next Monday at midnight to hand these in. In the meantime, if you have any questions, you can send me emails and I'll try to get back to you right away. And, but I think you'll have plenty of time to finish. Like I said, so far, and I'm still unfortunately not completely done with the corrections of the ones you've handed in. I'll be working on that over the next day or two. You can see your numbers, your scores in Moodle. There is actually a separate section in there where you can look at the grades that I put in. So as soon as I grade your problem sets, I type it right in there so you can see what they are. I've also posted the solutions so you can double check them if you want to. All right. So if nobody has any last minute questions, I guess I'll have to bid you a sad farewell because I think this is a great class and it's always sad when it's over. So does anyone have anything they want to ask? All right. Well, good luck with the problem sets. And you never know when I might see you again in the future. So, all right, here we go. One question. Oh, just to thank you. Well, you're absolutely welcome. Yes, this is one of my favorite classes, you can probably tell, because it's so logical. You don't see that in very many places in this world. But here in this little world of ours in statistics, everything is logical. And that's why it's so much fun. All right. So I guess I'll just have to say goodbye then. All right.